Recording. Nice. All right, let's do it. For real this time. All right, Brent, you're probably going to be the only person to watch this. All right. So some of the takeaways from my half of the presentation was that to accelerate, we need energy and we need power. And every time we transport or convert energy, we lose some of it to inefficiencies. So an efficient powertrain and a lightweight vehicle will maximize performance. And I want to go back to this slide where we talked about efficiency and give some numbers to it and talk about it, this slide from an accumulator standpoint. So first, this is a system that's 100% efficient with the accumulator, transfers the power to the motor controller, the drivetrain to the wheels. And in the case where there's 100% efficiency, all 25 kilowatts, for example, that are coming out of the accumulator are being used by the tires to propel the vehicle. That's our best lap time. But practically, there are many losses, and here are some example numbers for every system. Don't take them as exact truths because there's a lot of complications when it comes to efficiency. These are good ballpark numbers for each system. And what starts as 25 kilowatts at the accumulator ends up at only 20.5 kilowatts at the tires. So as we lose power, we lose the ability to use this energy or use this power to actually propel the vehicle. But another way of thinking about it is to get the same performance as 100% efficiency, we need to put out more power from the accumulator. So if we just increase that to 30.5, now at the tires, we're back to 25. So this is a way of thinking that if the vehicle is inefficient, it takes more power to perform as successfully or as high in performance. The rules limit the amount of power coming out of the accumulator, so we can't increase that if we have an extremely inefficient system. So that means the most efficient system can best use the 80 kilowatt maximum from the accumulator in terms of getting that to a tire. So clearly efficiency matters because the more efficient your vehicle is, the less energy you need to use for the same amount of performance. But stored energy comes at these three costs that we talked about yesterday. A battery costs a certain amount of money, a battery has a certain amount of weight, and a battery has a certain amount of volume. And those are all some of the most challenging aspects of building a battery pack and building an electric vehicle in general. So our first kind of design decision as an accumulator team is we have to choose the battery with the most optimal values for each of these costs. And there are more considerations to this. And in a future, I think probably next week, we'll talk about batteries more specifically, different types of batteries, different considerations. But this is one of our most foundational decisions that we get to make. So new stuff focusing on the accumulator are, if we zoom in to our battery pack, what are sources of inefficiency? How do these actually hurt the accumulator, hurt the cells, make me sad? And what are some design decisions we get to make to improve this? So we are starting just at the accumulator, and we're going to see how much energy, how much power we can put out to the motor controller. So the foundation of this is going to be efficiency is lost where there's resistance, where there's electrical resistance. There's no moving mechanical parts in the accumulator. We're just transferring electrical power from the battery out of the box. So if there's resistance, we lose voltage, and where we lose voltage, that's a loss in power. And if energy is not being used to propel the car or going out to the motor controller, we're losing it as heat. And that's really important because heat and high temperature is a critical component for, there's a critical potential for batteries being damaged, for components being damaged, and it drives all of our requirements for how we need to cool these things. And that's an extremely significant design challenge. So here's the equation we will consider. If power is your voltage times your current, and anytime there's a resistance, you're losing voltage. Anytime there's a resistance, you're going to lose power. And we're going to look at all the resistances in our battery pack and see how we choose them or where they come from and what we can do to maximize our efficiency. And when I say there's efficiency loss everywhere there's electrical resistance, we're going to be really detailed and dive into like every specific component. Some of these have really low resistances, some have much higher ones, but optimization means you look at everything first and figure out what's important. So the first is just the battery. And the battery is going to have some resistance internal to the cell. And we can look at data sheets, but most importantly, we can do testing. And James and Karen are doing a lot of important testing about how the resistance of the battery affects its efficiency. And that testing is really valuable because we have so many batteries in the accumulator. There are so many small sources of resistance where all of our power is flowing. So then the first thing that touches the cell is our cell connection. So we choose to use spot welded connection, but that's a design decision that we get to choose. And here's what they look like on Mark IV's accumulator. All those dots are the spot welded connections, and the quality of your spot weld will increase your efficiency if it's a higher quality. So the next thing are fusible links. So this step down is the fusible link between the cell and the main bus bar. And that's an interesting case because we actually use the fact that we're reducing or increasing the resistance to use that waste heat to actually break the piece of metal. So it's designed for safety, but we can't over design it from a safety standpoint and lose lots of energy to this resistance because it attaches to every single cell. So then after the fusible link, we have the actual bus bar. The material properties of that piece have some impact on its resistance, as well as the cross-sectional area. And then attached to the nickel bus bars are copper bus bars. And at the point where these two are touching each other, that contact point, there's going to be some resistance between those two. So we look at it from the side, there's the 6 bolt heads, and they are squeezing the copper and the nickel together. And the magnitude of that pressure, the clamping force, and the effective area, usually with a bolted joint, will increase or decrease the resistance. If you have higher pressure, you're going to get lower resistance. And if you want to talk about the analysis we did this year, Kasia is the person that did it and the person to talk to. Also, the condition of your part. So if you look at these two pieces, the one on the bottom is just how we machined it, how it ended up. And the one on the top is after we scrubbed it with a bunch of Scotch-Brite. And if your part is more flat and there's fewer impurities, you're going to get lower resistance and a more efficient connection. The copper bus bar itself has some resistance due to its cross-sectional area and its material properties. And you might think, okay, if we want the most efficient piece, we should just make the piece as big as possible. But now we have a trade-off with the weight. And that optimization process is a big challenge because on one side, you have the most efficient vehicle, but now it's heavier. On the other side, you have less efficiency, but now it's lighter. Then we have the service section. There are lots of components. There's lots of bolted joints. And every component is going to have resistance and every joint is going to have resistance. So if we have 4 pieces bolted together versus 1 continuous piece, that continuous piece will have generally lower resistance. Every joint's going to have resistance. Every component will have resistance. This picture on the right is an example of our main pack views, and you can see the 2 spots for connecting bolts, and every one of those spots is something you can analyze. So then the last thing before we finally get to the motor controller is outside the accumulator. We have high voltage wires, and these wires behave the same way as bus bars, where their size will dictate how much resistance they have, and they are generally very low sources of resistance, but that's because they need to be so large. So a note about the energy meter. The energy meter is a device that the rules and the competition uses to measure exactly how much power the accumulator is using. So they need a way of evaluating, is the vehicle exceeding the 80 kilowatt limit? And what's interesting is it's placed in the service section, which is kind of at the end of this path before power exits the accumulator. So if we can measure the voltage somewhere close by, it's actually better for us to be outputting more than 80 kilowatts at the battery, because we will lose some in all of these losses and all of these joints, all of these connections. And our goal is to get the spot where the energy meter is to read 80 kilowatts if we were measuring right there. So that's like a really, really cool optimization problem and a controls problem that we've never tried because we've never had a platform to test it. But it's something really cool we could do next year, and one of a ton of really cool things we could do in this space without having to redesign the entire car, and without having to, and something we can do now that we might have a lot more time to do testing. So this is like the full model, and like you can kind of see how everything happens together. There's bus bars, the cell connections, every component here is something we just talked about, and these are all decisions we get to make in designing this piece. This is from Mark IV. So some general conclusions. A powertrain with the highest efficiency is going to have the best performances, the best cost, and the best weight. There are many areas where we can have resistance in the accumulator, and it's generally the component of the entire vehicle where we have the most inefficiencies. And we also have the most number of decisions to make, the most components to choose, the most analyses to do, and the most parts to design. And every single one has some impact. So efficiency and weight generally at odds with each other. But all of this work and all this material has a lot of potential for analyzing things better, testing things better, and optimizing things. So that is all I had to talk about today. In future presentations, we might go into, or we will go into more specifics, kind of each component and other design considerations about them. But did any of this bring up questions, comments, things I forgot or missed that we want to talk about?
I have a question.
Yeah.
Could you go to the fusible link slide?
Yeah.
The one before that. Could you expand on the power loss to heat blows fusible link part of things?
Yeah. So the energy that we're losing to the resistance of that piece is going to go to heating it up. And that heat is going to increase the temperature until it reaches its melting point. And that's going to cause the link to physically blow up and separate to open the connection between the cell and the bus bar. So the same with the batteries. The energy that's lost to inefficiency goes to heating up the battery. So one thing we can do is try to minimize that energy that's being used to heat it up. And then the second thing is we can try to cool the battery to remove that energy to prevent it from heating. So having a good idea of how much the battery might heat up will design all of our design decisions about cooling, and is really important there.
Are fusible links like kind of the main way that most formula teams use to connect their cells, or are there like other more different options?
So the way we connect to the cell is actually the spot welded connection, and that can be, there's teams that do like wire bonding, which is, oh, what the heck? Can you still see anything? Can you see my screen again?
Mm-hmm.
The 18659. It's hard to see. I guess this is the best. So they have this bus bar, and they have this. This is their actual connection, and it's, I don't know what the exact name for the process that attaches them together is, but this little wire thing that attaches to the bus bar and the cell is what connects to the cell and acts as their fusible link. And this is actually from a team's battery pack, Purdue's battery pack, and they got a sponsor to do it for them. But it's just it takes way more machinery to do this process, and so we can buy a spot welder for our own and have all that control, whereas finding a sponsor and a company to do it is much harder. The rules also say like you can't do any non-permanent connections, or you can't, sorry, the rules say you can't solder to your cells, but there's also different types of cells that have different types of connections. So we used to use pouch cells, and they have these flanges coming off of them, and we connect them to other cells using just bolts or rivets. So it depends on what type of cell you have.
Can you not have non-permanent, or like, yeah, can you not have non-permanent connections like a cell holder and you just like plop them in?
I misspoke when I said that. It might be true, but I need to check the rules. I'm not totally sure.
It's like technically a bolt you could undo, right?
Yeah, I don't think they have to be permanently.
Yeah, no, you're totally right. Yeah, it's not that it's non-permanent. It needs to be positively retained if it's removable.
Yeah, but you are right. Oh, but what you were saying, it can't be soldered to. Because solder
so no
melt,
jank battery
so
pack soldering.
Yeah, right. Like you don't
like you're sticking a super hot iron right on your battery.
And also, like the solder itself, you don't want it to melt at a higher temperature and
yeah, good point.
Like break your connection.
Yeah, you're really shit out of luck.
The one thing I want to add to this presentation, which I think you did a really good job, is just kind of talking more about like electrical resistance. I think we've talked a little bit about how the resistance of a cell might change with temperature or state of charge, but electrical connections themselves, their resistance will change as well with temperature. So it's not, but it's the opposite. So with an increase in temperature, your electrical connections resistance tends to rise. And it's pretty linear for a small change in temperature. So that's just something we want to keep in mind for next semester when we're doing these tests, to know that as our pack is actually getting hotter, while our cells might be getting more, have a lower internal resistance, the electrical connections themselves might be increasing in resistance.
Why does that?
That's actually a really cool idea. And it has to do like the temperature coefficient of the material. So some materials will increase in resistance and some will decrease in resistance, depending on whether the temperature increases. I don't know if I can find a good resource on it. I don't know. But yeah. Do you know Katja, do you know like when is it important to look at how the temperature changes the resistance, or like I know we do it for the fusible links because the temperature changes like super high, but do you know like what the level of analysis is valuable or what we might do?
I'm not actually sure if it's that important. Like I don't have numbers. I know that like at small temperature changes, like the problems that we'll probably be seeing, the resistance is the changes linearly, which makes the calculations a lot easier. But I'm not sure if it's going to like change as much as the internal resistance of the cells that I think are a lot more variable. I like your kind of cheating the rules and making sure the energy meter doesn't go above 80 kilowatts.
Well, so like,
It's not
I
cheating,
think
but
2 years ago, that's like MIT's whole strategy was they had their own energy meter directly next to the FSC energy meter, and they used the energy meter there to tune exactly how much current is like the maximum that they can put out. So they were constantly optimizing as the race went on how much power they can actually put out to cells, and they ended up going over 80 kilowatts by like a couple tenths of a second, like literally such a small amount of time. And they got DQ'd from endurance despite that they wiped the floor with everyone. They came first in every single dynamic event, and they would have come first in the whole competition.
No.
But they got DQ'd. So clearly they had a winning race car, and that strategy might have been a huge part of that, but it is a touchy line to be on.
Yeah.
How does the energy meter measure the current?
I can answer that if you
Kache, you
want.
want to jump on that?
Oh, hey, Corey. Yeah.
I think Kache was going to answer.
Oh, cool, yeah.
Oh, you can go for it, Corey.
It uses there are a couple of different ways to measure current. You can infer current. Oh, you can't see my face. You can infer current using something to measure the electric field, which is what we do for one circuit in the car. But the more reliable way to do it is to use a shunt resistor, which is a resistance of a known but very, very small value. And then you just read the voltage across the resistor to tell you the current. So
But, like,
that's what they're, pardon?
the energy meter that we are given, like, how does that one specifically?
Correct. It uses a shunt resistor.
Like,
Yeah, it uses a shunt resistor, and the way it knows the voltage is we have to like connect. It has like a little like a free flowing wire on the side of it to connect to the other side of the bus bar, like the other side of the tractor system, so it can read the voltage, and then it just integrates. Like power is at current times voltage, so it just multiplies those two together. And if it senses that you're going above 80 kilowatts, so like it normally senses it at like 10 hertz or something, or 100 hertz. But if it senses you're going above 80 kilowatts, it'll do a quick burst of like a kilohertz or something to be like
I didn't know.
read
That's cool.
very, very fast, like to make sure it's like not to oversample in order for it to make sure it's not like you're reading the wrong value. So if MIT went over, it would have given a burst of really high frequency measurements to know, like to actually know and how well and how much they went over 80 kilowatts. Because like you need to go over 80 kilowatts for like 100 milliseconds or more, I think, like consistently or intermittently over the course of like half a second. But it's very specific rules on how long. If you go over for a millisecond, you're fine. But if you go over for more than like whatever duration it specifies over like a second, then you're done for.
I see.
It's so cool.
So if you could figure out like every time it would take a sample, you can just like offset going over and always miss it.
Yeah, that's one way to do it. And it's also why it also incentivizes you to use the data that the e-meter is reading, because ultimately that's what they're going to be judging you off of. So like that is an option. You can plug in like the network of the e-meter to the network of the car and you can read from it, but it just, yeah, but it's you have to like calibrate it and code that to happen. So it is work.
Yeah. Thank you.
Shall we move on?
Yeah. Thanks for listening, everybody. Thanks for your good questions.
You should have said, thanks for coming to my TED Talk on accumulator things.